We now plunge into the wild world of radicals and alkenes, which, believe me, can be somewhat confusing. And another aspect that's going to be a little confusing is that this mini lecture is going to appear before the other mini lecture, but you can still watch them in order. Okay, so this is where we're at. We have covered the background associated with radical chemistry and looked at kind of the basic radical reaction, which is that free radical halogenation of alkanes. Now, like I said, we're looking at what happens when we throw some alkenes into the picture. So the key to all of the radical chemistry in this chapter is to think about where the radical will form. And like I said before, this is going to become incredibly important when we start to look at mass spec. So we just saw that in free radical halogenation of alkanes, the most stable radical is the tertiary, followed by secondary, followed by primary. So the radical would form at the tertiary carbon preferentially, etc. Well, what happens then? How does that change when we throw a pi bond in the mix? Well, it makes perfect sense that when you throw a pi bond in there, the allylic hydrogen will be abstracted because that's a lot more stable there. And why is it stable? Because it's delocalized, of course. But, as usual, we're going to have some issues that appear, particularly in terms of selectivity, and we're going to have to think a little bit about what reagent we would use to carry out this chemistry. So selectivity-wise, yeah, it makes sense that if there's some way for this crazy, whoopsies, pardon me while I talk to myself here. There we go. If we can figure out some way to get this crazy pen to work, no, that's not what I meant. Some way to get that hydrogen, that allylic hydrogen, plucked off homolytically, well, then we've got our allylic radical. But then I dropped my pen. Oh my, there we go. This is going really, it's probably because there's a whiteout condition right now and everything's kind of freaking out here, including me. No, once we've formed our allylic radical, it can be delocalized as shown, and therefore, ay vey, when we react it with something else, it's kind of like what we saw when we were looking at allylic cations. We can end up with the expected product where the double bond hasn't shifted, or if we look at this resonance contributor and add a bromine here, well, then we get a completely different isomer. We'd expect to see two peaks in our GC. We'd see a messy mixture in our NMR. Ugh. So selectivity is kind of a big issue with allylic halogenation. Another question is, what reagent should we use? So we saw that in free radical halogenation of alkanes, we used bromine and some radical initiator like heat or light, maybe even a peroxide. But if we add bromine here, we got some serious issues because we'd expect it to add to the double bond. So it can't be bromine. So this is where NBS enters in. N-bromosuccinimide is the reagent for allylic halogenation. So NBS is an oddball. It's a source of electrophilic bromine. Well, what do we mean by electrophilic bromine? Well, bromine that's attacked by a nucleophile, right? So here is electrophilic bromine, which we've seen plenty of when our nucleophile is a set of pi electrons. It attacks to form the bromonium ion. So NBS is another source of electrophilic bromine, but here's the rub. It's not like adding a whole swampy equivalent of bromine. It just generates a tiny amount of bromine along the way as part of the reaction, and that's going to be the key to success in allylic halogenation. So N-bromosuccinimide has the best of both worlds. It's going to be a reagent that we'll see in radical chemistry because that N-nitrogen bromine bond is really easy to homolytically cleave, giving us the succinimide radical, which, to be honest with you, we don't care about that at all. This is our important piece. And it's a very useful reagent because the presence of N-bromosuccinimide allows for this low steady state concentration of Br2 to be formed. You'll see that the bromine is formed by the reaction of bromide with NBS to give you this anion fully delocalized. Wow, it's a terrific leaving group with that negative charge delocalized through this carbonyl and this carbonyl, and then Br2. So, mechanism. Well, the mechanism is in your text in great gory detail, but I think it might be useful to talk it through so we can kind of try and understand what's going on mechanistically in our HADES. Alright, so the obvious thing that would happen first if this is a radical reaction would be, of course, that we need to have something that can homolyze that nitrogen-bromine bond, and that can just be a little bit of heat, light of the right wavelength. That's a pretty easily cleaved bond. Once that's done, we get the bromine radical, Br dot, and that's our key player. That Br dot then is formed in the presence of the alkene, and as long as there's an allylic hydrogen present, that Br dot is going to abstract the allylic hydrogen to form that nice, stable allylic radical. At the same time, since Br dot abstracted a hydrogen, it has formed HBr. So that's where the HBr comes from to react with NBS, as we saw on the previous slide, to make the bromide, and that bromide reacts with NBS to make the Br2. So, the allylic radical, way back up here from step 2, then is present to react with the small amount of bromine that's present, and voila, you have your allylic brominated product. Now, as you look through the mechanism in detail in the text, you're probably scratching your head a lot, because it seems like it'd still be possible to form the dibromide. You've got HBr present, why couldn't you just make the monobromide? And obviously, this is our desired product. So what's going on? The whole key to this little balancing act is that it's a competition between all the possible pathways that can take place. Everything about this is completely governed by the fact that you have this low, steady state concentration of Br2. So, here's my low, steady state concentration of Br2, and basically, it can certainly react with cyclohexene to make the bromonium ion. That's not an issue at all. And will it? Of course it will. There's a tiny amount of this, there's tons of this. I would expect to see the bromonium ion. But at the same time, it can react with the allylic radical. Now this is going to be super fast. And the thing about this reaction is you're done. Bromine plus that radical, you're home free. The product is made. Whereas over here, first of all, this is a reversible reaction, so while the bromonium ion may be formed, it's also releasing to go back to bromine. At the same time, it has to react with bromide to go on to the 1,2 dibromo product. So the fact that this is reversible and the fact that this can happen very quickly leads to a preponderance of your allylic halogenation product. So just trust me, NBS works to give you the allylic product. Alright, so what do we got? If we have a substituted alkene like methylcyclohexene here, we now know we can do an allylic halogenation with NBS and maybe some heat or peroxides, but stand forewarned that this reaction actually isn't going to work well. Think about the other products that could form here. Because it's really going to be quite a mess. If I have methylcyclohexene and I want to go to the dibromide, what am I talking about here? Br2 and an inert solvent like carbon tetrachloride. Obviously, if I use water, I'd get the bromohydrin. If I use an alcohol, I'd get the bromine and the ether. Okay, how about I just want the mono halogenated cycloalkane? Well, we know that one. That's one of the back of your hand kind of reactions, electrophilic addition. Addition of HBr gives you carbocation intermediate and attack by the bromide onto the carbocation, which is of course formed as the most stable intermediate. So what's next? Well, now the last part of this chapter is learning a way to add HBr to the alkene in an anti-Markovnikov fashion. It ties in very well with what you've already learned. Basically, it's an example of radical chemistry and a change in mechanism. So what we didn't tell you before is that when you add HBr to your alkene to get the Markovnikov product, it's really kind of important to stipulate that it's in the dark. Because if you use light, which of course, as you know, is kind of screaming radical, then you're likely to get anti-Markovnikov addition. How in the world does that happen? So, when you get that kind of oddball result, you've got to think it's got to be a change in mechanism. But, take heart, even though we're going from a polar mechanism with our regular HBr addition, and by polar I mean carbocation intermediate, in this new mechanism where we have a radical intermediate, it's still following the rules. The most stable intermediate is always the one that is formed. So, what's the mechanism here? Well, you're going to see either light or peroxides, which is going to scream at you saying, oh yeah, this is going to be a radical reaction. That's going to be anti-Markovnikov as shown. So, first thing, initiation. We've got to generate a radical somehow, and that's what the peroxide is there for. With the peroxide present in that very weak peroxide linkage, piece of cake to break that OO bond and get two radicals. And initiation step. Propagation, well, with the radical present, now it's extremely easy for the peroxy radical to look for a hydrogen to abstract. Well, there it is. This is going to happen much more quickly than abstraction from the alkene. So I get, yay, my Br dot. And of course that's a reversible reaction. Br dot can abstract hydrogen from HBr, but you're just going back and forth. And eventually Br dot can come over here. And now what happens is that it adds to the alkene and gives you this free radical intermediate. And note, here's the difference in the regiochemistry. if it were our polar reaction, what adds first is the H, not the Br. And in so doing, we generate a secondary carbocation. But here the first thing that adds is the bromine, not the hydrogen. And so since the bromine adds first, we're still forming a secondary intermediate. It's just that it's the intermediate that is going to react with that HBr to give you your product. So, looks good. Initiation, lots of propagation steps, typical termination steps. So, I think the question that's probably sitting in your head right now is, dang it, this seems so arbitrary. Why doesn't the bromine dot, the radical bromine, remove the allylic hydrogen? We just saw that in allylic halogenation. Why wouldn't it do it here? Well, that's fine. It does. There's no reason why Br dot shouldn't abstract the allylic hydrogen and make the allylic radical. But again, this is a reversible reaction. And basically, Br dot is going to thermodynamically favor the formation of this product eventually. And this guy, because this is our stoichiometric reagent. So the fact that there's so darn much HBr present, this guy is just going to take you right back to your starting alkene, and then eventually that's where we end up. So I think that might be our last slide. But let me summarize these radical reactions. So free radical halogenation of alkanes so we're looking at no choice. They're all sp3 hybridized carbons and hydrogens. The radical is initiated by simple light-induced cleavage of bromine or chlorine. And as long as you're careful under your conditions, you will get monohalogenation. You've really got to worry about selectivity, though, when you have something that has primary, secondary, and tertiary hydrogens. Allylic halogenation requires N-bromosuccinimide. I mean requires. So it will be a 1-to-1 equivalency of N-bromosuccinimide to your alkene, and then you will get a preponderance of your desired product. But you really have to think about selectivity and the fact that even for this example, you could get some of this product. So I guarantee you the examples you'll see for allylic halogenations are things like this guy. Because then, you know what? There's only one possible outcome. Finally, our last but not least, anti-Markovnikov. Well, then you're talking about a 1-to-1 addition of HBr So you've got lots of HBr, lots of your alkene, a perfect one-to-one equivalency, but there's definitely going to be a radical initiator to induce the change in mechanism that will give you the anti-Markovnikov product. Radical reactions, especially these three, can be super confusing. Read the text, focus on the mechanisms, look at Cardy's explanations for the outcomes, and we'll do a fair amount of practice to help you get these cemented in your mind. Alrighty, see you in class.